In exascale AI training fabrics, simple network uptime is an obsolete metric. The key performance indicator that dictates the yield of AI tokens is Model Flops Utilization, or MFU. Consider the sheer scale of a state-of-the-art facility deploying 1 million interconnected GPUs. At this density, factoring in amortized hardware and facility power, the baseline operational cost is $4 million every hour. Because of that extreme burn rate, a single % drop in MFU strands $40,000 of capital expenditure per hour. At the 1 million node threshold, network efficiency acts as the primary mathematical governor of hyperscaler profit margins. Smaller clusters, operating around 10,000 GPUs, routinely maintain an MFU of 55%. But as node counts approach 1 million, the physics of network scaling degrade nonlinearly. Standard reactive routing protocols, like BGP and ECMP, inevitably trigger localized congestion microbursts during intense synchronization phases. These localized collisions cascade upward rapidly, choking the primary data pathways and causing massive stalls at the spine layer. Without intervention, this physics problem forces the average MFU across a standard exascale fabric to collapse to roughly 35 to 40%. By relying on traditional shortest path network designs, data center operators strand nearly half the value of their multi-billion-dollar infrastructure. A major contributor to this efficiency collapse is the prevalence of gray failures, things like degrading optical transceivers or silent packet drops that slowly bleed network performance. The industry standard for tracking these issues is Simple Network Management Protocol, or SNMP polling. SNMP relies on checking individual endpoints against rigid, scalar thresholds to identify hard system breaks. But in an environment with 1 million nodes, the data signature of a degrading component is mathematically indistinguishable from normal background noise. Because they operate below the hard IT alert thresholds, these failures persist for an industry average of 4.5 hours before being flagged. Millions of dollars in compute time are lost before the system even registers an error, proving that reactive scalar polling fails at exascale. The solution is to model the entire data center's telemetry state as a continuous quantum density matrix using the Tensor-Network Quantum Gravity, or TNQG framework. Instead of polling individual nodes, TNQG calculates the quantum relative entropy of the global network state. This technical paper outlines the formula used to detect structural anomalies. Look closely at the variables. It measures the divergence between the observed operational state, sigma ops, and the pristine modeled state, rho model. Under TNQG, a gray failure is a structural topological defect. When the relative entropy calculation spikes, it provides instant mathematical proof that a specific rail or spine link is compromised. This shrinks the time to detect from 4.5 hours down to a matter of milliseconds. By identifying compromised pathways instantly, the TNQG framework isolates the failure and stops the utilization bleed before it cascades. Identifying a structural defect is only valuable if the system can instantly route traffic around it. This is where the Predictive Tensor Control Plane, or PTCP, steps in to execute the detection. Calculating new routing paths across 1 million endpoints simultaneously would normally overwhelm any data processing unit. PTCP solves this dimensionality problem by compressing the data center's massive telemetry into a pattern-of-life tensor train. This compression achieves bounded memory execution with a specific operational complexity of O of dnr squared. Because the memory requirement is strictly bounded, standard ConnectX-8 DPUs run the calculations without processor overload. Once a defect is flagged, PTCP calculates the conditional value at risk to preemptively shift traffic onto stable alternative infrastructural routes. During massive all-to-all synchronization phases, it actively smooths out traffic gradients before switch buffers overflow. Ultimately, PTCP acts as the active immune system for the network, mathematically neutralizing the microbursts that traditionally crash exascale operations. To test this, researchers conducted a 24-hour simulation scaling to 1 million GPUs, running a continuous 1 trillion parameter training workload. This table directly compares the results of a standard reactive control setup against the integrated PTCP and TNQG topological plane. The top row shows the standard architecture failing. It degraded to a 38.5% average NUF, stranding over $1.4 million an hour. The middle row tracks the PTCP and TNQG system, which successfully maintained a flat, optimized utilization profile of 55.2%. Looking at the net difference row, the integrated topological plane yielded a recovery of 16.7% MFU. That efficiency gap is a staggering operational victory, translating directly into an additional 6.96 trillion AI tokens generated every single second. Those recovered tokens translate directly back into the core economic metric for data center operators, capital expenditure. The simulation data proves that the topological framework successfully unstrands $1,113,333 in CapEx every single hour of operation. Extrapolated across a full operational year, the final cumulative impact is $8.76 billion in total unstranded infrastructure value. This level of recovery represents a return on architecture that effectively subsidizes the initial hardware procurement over the facility's lifecycle. Attempting to operate 1 million node exascale fabrics as localized shortest path switches simply guarantees economic failure. By integrating quantum defect detection and predictive tensor actuation, operators mathematically bound their risk, recovering billions in capital and establishing the million node data center.